Please subscribe to support the channel. When we look up at the night sky, the stars appear as tiny pinpoints of light, gentle twinkles scattered across the dark canvas above us. But hidden among them are titans of unimaginable size, stars so vast and powerful that even our sun, which sustains all life on Earth, seems insignificant in comparison. Among these cosmic giants, one name stands out in particular: KY Cygni. KY Cygni is not a household name like Betelgeuse or Rigel, yet it is one of the most fascinating and extreme stars ever discovered. This massive red supergiant has earned recognition as one of the largest known stars in the universe, a true colossus that defies the limits of our imagination. Unlike ordinary stars that can be studied with relative ease, KY Cygni is so enormous and so distant that it challenges even the most advanced astronomical techniques. And yet, despite the difficulties, astronomers have been able to paint an astonishing picture of this star's scale, nature, and ultimate destiny. At its core, KY Cygni is a red supergiant star, meaning it has expanded to incredible proportions as it nears the end of its life cycle. What makes KY Cygni especially intriguing is not just its size, but the mystery surrounding its exact measurements. Estimates of its radius suggest it could be around 1,400 times larger than the Sun, though some calculations put it slightly smaller. To put this into perspective, if KY Cygni were placed at the center of our solar system, its surface would stretch well past the orbit of Jupiter, swallowing Mercury, Venus, Earth, Mars, and even the asteroid belt with ease. It is so vast that trying to fully comprehend its dimensions almost feels impossible. But size is not the only reason astronomers pay such close attention to KY Cygni. Stars like this one are essential to understanding the life cycles of the most massive stars in the cosmos. Unlike our Sun, which is relatively stable and will spend billions of years slowly burning its fuel, KY Cygni is in a fast-burning, unstable phase of stellar evolution. This makes it a cosmic laboratory for studying how giant stars live, die, and ultimately give back their material to the universe. KY Cygni also belongs to a special group of stars known as variable stars. Its brightness changes over time, adding another layer of complexity to its behavior. These fluctuations, combined with the surrounding dust and gas that obscure it, make KY Cygni difficult to study with precision. Yet these very challenges make it a thrilling object for scientists. Every observation, every new calculation, brings us closer to unlocking the secrets of how stars at the upper size limits of the universe evolve. Perhaps the most remarkable aspect of KY Cygni is how humbling it feels to even think about it. It exists so far beyond our everyday scale of understanding that the only way to grasp its immensity is through metaphors, comparisons, and numbers that strain the human imagination. This star reminds us that the universe is not only vast but also filled with extremes that dwarf our entire solar system. In the grand tapestry of the cosmos, KY Cygni stands as a shining example of just how extraordinary stars can be when they push the boundaries of physics and scale. In order to truly appreciate the enormity of KY Cygni, it helps to first ground ourselves in its place within the cosmos. Knowing where a star resides in the galaxy gives us a sense of context: how far away it is, what part of the Milky Way it calls home, and what surrounds it. This perspective transforms KY Cygni from just a set of numbers and measurements into something we can better connect with as part of our shared universe. KY Cygni resides in the constellation of Cygnus, also known as the Swan. Cygnus is one of the most recognizable constellations in the northern sky, stretching across the rich band of the Milky Way that arcs overhead on clear summer nights. The constellation itself has been a fixture of mythology for thousands of years, often depicted as a graceful swan flying through the heavens with wings outstretched. Within this celestial swan lies not only some of the most iconic stars we can see with the naked eye, like Deneb, one of the brightest stars in our sky, but also a treasure trove of hidden wonders, including KY Cygni. Now, the star is located roughly 5,000 light-years away from Earth, a distance that defies everyday comprehension. To put it in perspective, a light-year is the distance light travels in 1 year, about 5.88 trillion miles, 9.46 trillion kilometers. Multiply that by 5,000, and you begin to grasp the sheer vastness separating us from KY Cygni. Even if we were somehow able to travel at the speed of light, a speed currently beyond the capabilities of any technology or physics we know, it would still take 5 millennia to arrive at this star. That means the light we see from KY Cygni tonight actually left the star around the year 3000 BC, during a time when ancient civilizations were just beginning to construct monumental structures like the pyramids of Egypt. In other words, looking at KY Cygni is like looking back in time thousands of years. The region of Cygnus where KY Cygni resides is not just home to this one star. Cygnus is part of what astronomers often call the galactic plane, the densely packed disk of our Milky Way galaxy where stars, nebulae, and clusters abound. This region is rich in interstellar dust and gas, which is both a blessing and a curse for astronomers. On one hand, it is the perfect environment for forming new stars and understanding stellar life cycles. On the other, the thick dust clouds obscure our view of stars like KY Cygni, making it harder to pin down their exact size, brightness, and structure. This obscuration is one of the reasons why KY Cygni doesn't shine as prominently in the night sky despite its enormous size. It's hidden behind veils of cosmic dust, visible only with careful observation through advanced telescopes. Another fascinating aspect of KY Cygni's galactic neighborhood is its relationship to other massive stars in Cygnus. Cygnus itself is a stellar nursery of sorts, filled with young, hot stars and aging red supergiants like KY Cygni. This makes it a particularly interesting area of the sky for astronomers studying how stars are born, evolve, and die. Being located in this constellation means KY Cygni is part of an environment where stars constantly interact with their surroundings, blowing off winds, creating shockwaves, and stirring up the interstellar medium. It's worth noting that the sheer distance of KY Cygni poses incredible challenges for astronomers. Even though it is one of the largest stars we know of, it is too far away to observe in detail with the naked eye. Unlike bright stars such as Betelgeuse in Orion, which can be spotted easily without equipment, KY Cygni remains hidden from casual stargazers. Only through professional observatories and instruments capable of cutting through the dust and distance can astronomers study it. Yet this very challenge is part of its allure. It represents a frontier in our exploration of the galaxy, something vast, mysterious, and just out of reach, demanding our best scientific efforts to unlock its secrets. Being in the constellation Cygnus also places KY Cygni in a part of the sky that is already deeply significant in astronomy. Cygnus is home to the famous Cygnus X region, one of the strongest sources of X-rays in the galaxy, as well as the Cygnus loop, a supernova remnant that gives us a glimpse of what stars like KY Cygni might eventually leave behind. In a way, KY Cygni sits among both the beginnings and endings of stellar life cycles, surrounded by young star-forming regions and ancient remnants of stellar explosions. Its presence in this region reinforces the idea that Cygnus is a microcosm of the galaxy itself, a window into the diversity and drama of stellar evolution. When you step back and consider it, the fact that KY Cygni resides so far away yet still demands our attention is itself remarkable. Our ability to detect, study, and theorize about a single star 5,000 light-years away speaks volumes about human curiosity and ingenuity. We are, in essence, peering across the galaxy to study a giant whose story is still unfolding, whose light has traveled thousands of years just to reach our eyes and instruments. And this brings us naturally to the next question. Just how big is this distant giant? Knowing where KY Cygni is located in the galaxy is crucial, but what truly captures the imagination is its sheer size. When we compare KY Cygni to our Sun and place it within the framework of our solar system, the scale becomes staggering. So, let us now transition from where KY Cygni is, to the astonishing reality of how big it really is. Having located KY Cygni within the constellation of Cygnus, roughly 5,000 light-years away, we can now focus on one of the most jaw-dropping aspects of this star, its size. Size is what sets KY Cygni apart from almost everything else in the universe we've observed. It is not simply large, it is colossal, a behemoth that stretches the very boundaries of how we define stars. While many stars dazzle us with their brightness or exotic properties, KY Cygni stuns astronomers and enthusiasts alike because of its sheer, incomprehensible bulk. Let's start with the raw number. KY Cygni is estimated to have a radius up to 1,400 times that of our Sun. Now, it's easy to hear that figure and nod along, but what does that really mean? Numbers alone don't quite capture the enormity of such a star, so let's break it down with comparisons and visualizations that bring the scale into focus. Our Sun, the star that provides Earth with warmth and energy, has a radius of about 432,000 miles, 696,000 kilometers. Multiply that by 1,400, and KY Cygni's radius could stretch to an almost inconceivable 600 million miles, 965 million kilometers. That's not just big, it's solar system swallowing big. If we placed KY Cygni at the center of our solar system where the Sun is now, its outer edge wouldn't just reach Mercury, Venus, Earth, and Mars. It wouldn't stop at the asteroid belt. It would extend beyond Jupiter's orbit, a distance so immense that it's hard to fully appreciate without a guided mental journey. Imagine this: Earth orbits the Sun at a comfortable 93 million miles, 150 million kilometers, away. To us, that feels like an unfathomable distance, but in cosmic terms, it's just a small step. Now picture KY Cygni's surface engulfing that space entirely. Earth, Venus, Mercury, and Mars would be deep inside this star. Even Jupiter, which orbits at about 484 million miles, 778 million kilometers, from the Sun, would find itself dangerously close to KY Cygni's outer atmosphere. If KY Cygni were in the Sun's place, the solar system as we know it would be utterly transformed. Planets we consider outer worlds would be swallowed whole, and icy moons like Europa, Ganymede, or Callisto might orbit within its fiery atmosphere. Let's put it another way. If you could somehow shrink the Sun down to the size of a soccer ball, KY Cygni in comparison would be more like a skyscraper taller than Mount Everest looming beside it. Or if you think in terms of everyday travel, light itself, the fastest thing in the universe, would take over an hour to travel from one side of KY Cygni to the other. By contrast, it takes light just over 8 minutes to reach us from the Sun. This gives you an idea of how mind-bendingly vast KY Cygni truly is. Now consider what it would mean to physically see a star that size up close. If you were somehow orbiting around KY Cygni at the same distance Earth is from the Sun, the star would not merely dominate the sky, it would fill your entire view. There would be no night, no stars, no darkness at all. The star's disk would stretch across the sky from horizon to horizon, a red expanse so overwhelming that it's hard to imagine life of any kind surviving anywhere near it. And yet, stars like KY Cygni are not only real but also critical to the galactic ecosystem. Its size also raises fascinating physical questions. How can a star expand to such a size without simply tearing itself apart? The answer lies in the delicate balance of forces at play within a red supergiant. Deep in its core, nuclear fusion is pushing outward, while gravity tries to pull everything inward. In smaller stars like the Sun, this balance keeps them compact and relatively stable. But in stars like KY Cygni, the immense energy produced by fusion causes their outer layers to expand and puff outward into space, creating an extended and diffuse atmosphere. This is why KY Cygni, despite its size, has a very low density compared to smaller stars. You could say it's fluffy, a giant ball of gas with matter spread so thin that if you were somehow inside it, the star's material around you would feel more like a tenuous cloud than a solid wall of heat. Another striking aspect of its size is how it fits into the broader population of massive stars. KY Cygni is among the largest stars ever measured, rivaling or surpassing other famous giants like Betelgeuse or VY Canis Majoris. And while astronomers debate the exact measurements, because dust, distance, and variability make it hard to calculate with perfect precision, there is no doubt that KY Cygni ranks among the largest known stars in the entire universe. Its radius alone puts it in the extreme upper tier of stellar sizes, making it a valuable case study for understanding the limits of stellar expansion. One of the challenges with imagining something this vast is scale distortion. Human brains aren't wired to comfortably process millions of miles. So let's break it down one last way. If you could line up Earths across KY Cygni's diameter, you could fit over 2,800 Earths from one side to the other. That's not counting volume, just a straight line across. And if you consider volume, KY Cygni could fit over 3 billion suns inside of it. That's billions, not millions. Suddenly, even our Sun, which itself is large enough to fit 1.3 million Earths inside, looks puny and fragile by comparison. This perspective is both thrilling and humbling. KY Cygni doesn't just redefine what big means, it shatters the very notion of scale as we know it. Standing on Earth, looking at the Sun in our sky, we might think it's the largest, most powerful thing we can imagine. But KY Cygni reminds us that even our life-giving star is just a tiny ember in the vast ocean of cosmic fire. And yet, despite this overwhelming immensity, KY Cygni is not the hottest, nor the brightest, nor even the most massive star in the galaxy. That leads us to another fascinating layer of its story: its surface temperature. For all its enormity, KY Cygni burns relatively cool compared to smaller, hotter stars. Its fiery red glow tells us a great deal about its character and the strange physics governing these cosmic titans. Let's now shift from discussing its incredible size to exploring the nature of its surface and why being so big does not necessarily mean being so hot. Having unraveled the staggering enormity of KY Cygni's size, it's only natural to assume that such a star must also burn with extraordinary heat. After all, in our everyday experience, bigger fires burn hotter, brighter, and more intensely. Yet here is where KY Cygni surprises us once again. For all its colossal size, KY Cygni is actually relatively cool compared to many other stars, even smaller ones. This contradiction between size and temperature is one of the most fascinating aspects of its nature and a window into the physics of red supergiants. KY Cygni's surface temperature has been measured at around 3,500 Kelvin. To put that in more familiar terms, that's roughly 3,200 degrees Celsius or about 5,800 degrees Fahrenheit. Now, those numbers sound unimaginably hot from a human perspective. After all, steel melts at around 1,500 degrees Celsius, and the hottest lava flows on Earth top out at just over 1,200 degrees Celsius. By our standards, KY Cygni's surface is blisteringly hot, far beyond anything we could endure. But in stellar terms, this temperature is on the cooler end of the scale. Our Sun, for example, has a surface temperature of about 5,778 Kelvin, making it significantly hotter than KY Cygni despite being vastly smaller. Blue giants, like Rigel in Orion, can burn with surface temperatures exceeding 20,000 Kelvin, and some stars go even hotter. So why is KY Cygni, this gargantuan red supergiant, glowing at such a modest temperature compared to its smaller counterparts? The answer lies in its evolutionary stage and the physics of how stars maintain equilibrium. Stars are essentially massive nuclear reactors, balancing two opposing forces: the outward push of energy from nuclear fusion in their cores and the inward pull of gravity trying to collapse them. When stars like KY Cygni reach the red supergiant stage, their cores have already used up much of their hydrogen fuel. Fusion shifts to heavier elements, and the balance between gravity and outward pressure changes dramatically. The result is that the star expands, ballooning outward to incredible sizes. But as it expands, its surface area increases enormously, and the energy from the core gets spread across this vast expanse. This causes the outer layers to cool down relative to smaller, more compact stars. That cooling effect is what gives KY Cygni its red color. Stellar temperature directly influences color. Hotter stars shine blue or white, while cooler stars glow red or orange. KY Cygni's deep red hue is the visual signature of its relatively low temperature, a sign that it has entered a late and unstable phase of stellar evolution. When astronomers look at KY Cygni, they see not the piercing brilliance of a blue giant, but the softer, smoldering light of a star nearing the end of its life. One of the fascinating consequences of this temperature is how it affects the star's luminosity. You might assume that being so large automatically makes KY Cygni the brightest star in the galaxy, but brightness is not just a function of size. It's also dependent on temperature. Smaller but hotter stars can shine more intensely because their surfaces radiate far more energy per unit area. This means that KY Cygni, despite being one of the largest stars known, is not necessarily one of the brightest when compared to blindingly hot blue stars. Its light, though immense, is relatively gentle when spread across the night sky. Gentle enough, in fact, that it is invisible to the unaided eye. Yet even at only 3,500 Kelvin, KY Cygni is still incredibly luminous by human standards. Astronomers estimate it to be tens of thousands of times brighter than our Sun. The sheer size of its radiating surface compensates for the lower temperature, allowing it to pour staggering amounts of energy into space. It's like comparing a giant bonfire to a small blowtorch. The blowtorch burns hotter, but the bonfire, by sheer scale, produces more total heat and light. KY Cygni is the cosmic equivalent of that bonfire, sprawling, diffuse, and less intense per square inch, but absolutely dominating in total output. The surface temperature also hints at the complex atmospheric structure of KY Cygni. Unlike compact stars, which have relatively well-defined surfaces, red supergiants possess extended, turbulent atmospheres with convection currents the size of planets. These massive upwellings of gas, driven by the star's inner fusion processes, rise to the surface and cool as they expand outward. This creates dramatic temperature variations across different regions of the star. Imagine bubbles of hot plasma the size of Earth rising and bursting on the surface. KY Cygni's outer layers are anything but uniform. Another intriguing aspect is how its temperature interacts with the dust and gas surrounding the star. At 3,500 Kelvin, the radiation from KY Cygni is strong enough to heat nearby material but not strong enough to blow all of it away completely. This allows dust to condense and form in its outer atmosphere. That dust eventually escapes into the interstellar medium, where it contributes to the raw material for forming new stars and planets. In a very real sense, KY Cygni's relatively cool temperature plays a direct role in how it seeds the galaxy with matter. From a scientific perspective, KY Cygni's temperature gives astronomers valuable insights into the life cycle of massive stars. The red glow is a telltale sign of a star that has moved beyond the main sequence, exhausted much of its hydrogen, and is now in the process of burning heavier elements. It's an outward symptom of an inward struggle. The star's core is undergoing intense nuclear reactions, while its outer layers balloon outward and cool. This precarious balance is what makes red supergiants like KY Cygni so unstable and short-lived compared to smaller stars like the Sun. And so, despite being a cosmic titan that dwarfs our solar system in scale, KY Cygni glows with a gentle, red light rather than an overpowering blue-white blaze. It reminds us that in the universe, bigger does not always mean hotter or brighter. In fact, the contrast between KY Cygni's enormous size and relatively low temperature is what makes it such a compelling object of study. It challenges our intuitions and pushes us to think beyond simple assumptions about how stars behave. But this naturally leads us into the next fascinating layer of its story: brightness versus size. How does a star that's so massive and so vast stack up against other stars when it comes to sheer luminosity? Why can smaller stars often outshine giants like KY Cygni? And what does this tell us about the delicate interplay between temperature, size, and brightness in the life of a star? These questions bring us to the next chapter in our exploration of this extraordinary supergiant. We've explored KY Cygni's astonishing size and its relatively cool surface temperature of around 3,500 Kelvin. But now we arrive at an even more thought-provoking contrast: its brightness versus its size. When we imagine something that is larger, we naturally think it should also be more powerful, more luminous, and more commanding in every way. In daily life, bigger light bulbs emit brighter light, larger fires produce more heat, and bigger speakers blast louder sound. Yet KY Cygni defies this simple logic. For all its unimaginable immensity, it is not among the brightest stars in the galaxy. Smaller, hotter stars often outshine it, even though they are physically much tinier. This apparent contradiction is one of the most fascinating aspects of stellar physics. To understand why, we need to examine the concept of stellar luminosity. Luminosity is a measure of how much total energy a star emits per second. It depends on two main factors: the star's surface area, which is a function of its size, and its surface temperature, which determines how much energy each square meter radiates. The mathematical relationship between these is described by the Stefan-Boltzmann law, which tells us that luminosity is proportional to the surface area times the temperature raised to the fourth power. This means that while size certainly increases a star's luminosity, temperature is a far more powerful factor. Because luminosity depends on the fourth power of temperature, even small increases in surface heat lead to massive jumps in brightness. For instance, if one star is twice as hot as another, its surface radiates 16 times more energy per unit area. That's why compact, blue stars can shine more brilliantly than enormous red supergiants like KY Cygni. Let's apply this to KY Cygni. With a surface temperature of around 3,500 K, it radiates far less energy per square meter than our Sun, which sits closer to 5,800 K. Despite this, KY Cygni's gargantuan size gives it a tremendous overall luminosity, estimated to be tens of thousands of times greater than the Sun's. This is because its vast surface area compensates for the lower energy output per unit area. Still, compare KY Cygni to a much hotter star like Rigel in Orion. With a surface temperature of about 12,000 K, Rigel is smaller than KY Cygni, but its high temperature allows it to pour out vastly more energy, making it one of the brightest stars visible in the night sky. KY Cygni, by contrast, is invisible to the naked eye without a telescope, largely because its energy is spread across the cooler, redder part of the spectrum and because it sits enshrouded in dust nearly 5,000 light-years away. This is why KY Cygni does not dazzle us in the sky like some of its smaller but hotter counterparts. Its sheer immensity ensures it radiates colossal amounts of energy, but because that energy emerges as cooler, redder light, much of it isn't as easily detectable to the human eye. Our vision is most sensitive to yellow-green light, around the same wavelength where the sun emits the most. A star like KY Cygni, glowing faintly red, doesn't have the same piercing brilliance from Earth's perspective, even though it is objectively one of the most powerful sources of energy in the cosmos. Another factor limiting KY Cygni's apparent brightness is its distance and dust environment. At roughly 5,000 light-years away, its light has to travel an immense distance through the dense, dusty plane of the Milky Way. Interstellar dust tends to scatter and absorb shorter wavelengths of light, but even red light gets dimmed. As a result, KY Cygni's glow is further muted, hiding its true radiance from our eyes. If this star were as close to us as Betelgeuse, about 642 light-years away, it would likely rank among the most striking stars in the sky. But brightness isn't just about visibility. It also reveals something profound about a star's internal life. Stars like KY Cygni, enormous but relatively dim compared to smaller, hotter stars, are at a stage where their internal fusion processes are no longer as efficient as before. They are bloated, expanded, and cooled, with much of their energy output being spread thin across a massive surface. This inefficiency is a sign that KY Cygni is in a late evolutionary stage, one where it is nearing its inevitable collapse and fiery end. Its dimmer light is, in a way, the quiet whisper of a star that has burned through much of its prime fuel and is now living on borrowed time. Now, think about this contrast again in human terms. Imagine standing next to a roaring blue blowtorch flame. It's compact, focused, and searingly hot. That's like a smaller, hotter star. Then imagine a massive campfire, sprawling and crackling but less intense in its heat at any single point. That's KY Cygni, enormous, diffuse, and less concentrated in its power. The campfire covers a bigger area, and if you add up its total heat, it's still tremendous, but the experience of standing near it feels less blindingly intense than that small but fierce blowtorch. This comparison between brightness and size also reshapes how we view our own Sunday. Against KY Cygni, the sun looks like a speck, but in terms of temperature, the sun is hotter, and its light is perfectly tailored to human vision. If KY Cygni sat where our sun is now, it would certainly engulf the inner planets with its sheer size, but the light falling on Earth, if Earth somehow still existed, would be dimmer and redder, far less conducive to supporting the kind of life we know. This paradox, giant stars that are not the brightest, adds to KY Cygni's allure as a subject of study. It demonstrates that the universe doesn't always conform to our intuitive rules. Size alone doesn't dictate brightness. Temperature is the hidden master of a star's light. KY Cygni serves as a perfect case study in this truth. And this contrast naturally sets the stage for another fascinating line of thought. What happens when we compare KY Cygni directly with our own sun? We've already touched on some of the differences, but putting them side by side, considering not just their sizes, but their appearances, temperatures, and roles, brings the unimaginable scale of KY Cygni into even sharper focus. We've now seen how KY Cygni's size and temperature give it a very different profile than smaller, hotter stars, but to truly grasp its scale, there's no better comparison than our own Sunday. The sun is the star we know best. It is the anchor of our solar system, the giver of light and life, and to us it feels impossibly vast. Yet when placed side by side with KY Cygni, the sun suddenly shrinks into something almost negligible, a cosmic ember next to a raging inferno. Our sun has a radius of about 432,000 miles, 696,000 kilometers. That's large enough to fit about 109 Earths across its diameter. It's also massive enough to contain 1.3 million Earths by volume. To us, this scale is staggering. But KY Cygni takes those numbers and makes them feel trivial. With a radius up to 1,400 times larger than the sun, KY Cygni's volume could contain more than 3 billion suns. That's right, billions. When you picture the Sun as a glowing ball of fire in the middle of our solar system, remember that KY Cygni could swallow it whole, along with every single planet up to Jupiter, without even breaking a sweat. Imagine the Sun reduced to a glowing orange marble. Next to it, KY Cygni would not be a basketball, or a beach ball, or even a house-sized sphere. It would be more like a city-sized dome towering over a pebble. In fact, if the Sun were the size of a coin, KY Cygni would be the size of a football stadium. The difference is so extreme that it defies our sense of proportion. The Sun, which feels to us like the center of everything, would look like a mere speck against KY Cygni's vast, bloated expanse. Another striking comparison lies in light and color. The Sun's surface temperature of nearly 5,800 Kelvin gives it a brilliant white-yellow glow, the kind of light perfectly suited for life on Earth. KY Cygni, however, with its cooler surface of 3,500 Kelvin, would appear as a deep, blood-red star. If you could place the two stars side by side in space, the Sun would shine brighter per square meter, but it would be utterly dwarfed in size. To the naked eye, it would almost look like a bright dot plastered onto KY Cygni's immense crimson disk. The difference in scale also reshapes our understanding of energy output. The Sun provides every photon of light, every ounce of heat, and every bit of energy that sustains life on Earth. It feels like the most powerful object imaginable. Yet KY Cygni radiates tens of thousands of times more total energy simply because of its sheer size. While each square meter of KY Cygni's surface emits less energy than the Sun, the sheer number of square meters, trillions upon trillions of them, makes its overall luminosity vastly greater. The Sun is like a small but intense lamp, while KY Cygni is a sprawling bonfire stretching across half the sky. And let's not forget gravitational influence. Our Sun holds the entire solar system together with its mass. Planets, comets, and asteroids all orbit within its gravitational embrace. But KY Cygni's mass, although immense, is not as overwhelming as its size might suggest. Astronomers estimate KY Cygni's mass to be perhaps 25 to 30 times that of the Sun. That's a lot, but far less than you'd expect given its volume. This is because KY Cygni is extremely diffuse. Its outer layers are spread so thin that if you somehow stood inside them, the star would feel more like a tenuous cloud of gas than a solid wall of heat. Compared to the dense Sun, KY Cygni is more of a cosmic balloon, large and puffy, but surprisingly low in density. Thinking about these comparisons is humbling. For us, the Sun is everything, the source of day and night, seasons, warmth, and photosynthesis. Without it, Earth would be a frozen wasteland adrift in the dark. Yet KY Cygni reminds us that our Sun is just one small, ordinary star in a galaxy filled with extremes. If KY Cygni were placed in the Sun's position, our solar system as we know it would not exist. Mercury, Venus, Earth, and Mars would be swallowed whole. Jupiter would hover just at the edge of its surface, possibly inside its atmosphere. Life as we know it could never arise in the blazing, all-encompassing glow of such a giant. This isn't just a thought experiment, it's a perspective shift. By placing the Sun next to KY Cygni, we realize how modest our star truly is. And yet, that modesty is precisely what makes life possible. The Sun is stable, predictable, and long-lived. Stars like KY Cygni may be awe-inspiring in their size, but they live chaotic, short lives, burning through their fuel in a cosmic blink of an eye before collapsing in fiery supernovae. The Sun, in contrast, will shine steadily for billions more years, providing Earth with the stability life needs to flourish. So when we compare the Sun to KY Cygni, we see both the extraordinary scale of the universe and the delicate balance that makes our existence possible. The Sun may be small by cosmic standards, but it is just right for us. KY Cygni, on the other hand, represents the extremes, a titan among stars, a giant nearing the end of its life, a reminder of both the grandeur and the violence of stellar evolution. And of course, KY Cygni is not alone in this category of cosmic behemoths. To fully appreciate its place in the stellar hierarchy, we need to compare it with other famous giants. Stars like Betelgeuse, UY Scuti, and VY Canis Majoris. How does KY Cygni measure up against its colossal cousins? Which one truly deserves the title of the largest star in the universe? This comparison will give us a deeper sense of where KY Cygni stands in the gallery of stellar extremes. Having contrasted KY Cygni with our familiar Sun, it becomes even more intriguing to place it within the broader context of other stellar giants. The universe is home to a handful of stars so massive and enormous that even our Sun, gigantic in human terms, seems minuscule by comparison. Stars such as Betelgeuse, KY Cygni, and KY Canis Majoris are among the most famous, each a cosmic colossus in its own right. Comparing KY Cygni with these giants allows us to understand not only its size but also its uniqueness in the spectrum of supergiants. Let's begin with Betelgeuse, perhaps the most well-known red supergiant, famous not only for its size but for its visibility in the night sky. Betelgeuse sits in the constellation Orion and has been a subject of fascination for astronomers for centuries. Its radius is estimated at around 950 to 1,200 times the Sun's radius, making it slightly smaller than KY Cygni, though the two are within a similar scale range. Betelgeuse, like KY Cygni, is a red supergiant nearing the end of its life, characterized by a relatively cool surface temperature of roughly 3,500 to 3,600 Kelvin, giving it a deep orange-red hue. However, unlike KY Cygni, Betelgeuse is much closer to Earth, approximately 642.5 light-years away, which is why it is visible as a prominent, distinctly reddish star in the night sky. This proximity has allowed astronomers to study Betelgeuse in far greater detail, observing surface turbulence, giant convection cells, and irregular pulsations that hint at the complex physics of red supergiants. Next, consider KY Canis Majoris, an extreme example of a red hypergiant located in the constellation Canis Major. Its estimated radius ranges from 1,300 to 1,500 times the Sun's radius, which puts it in a size bracket comparable to or even slightly larger than KY Cygni. KY Canis Majoris has an irregular, highly extended atmosphere, and like KY Cygni, it is surrounded by a substantial envelope of gas and dust. Its luminosity is staggeringly high, over 270,000 times that of the Sun, despite having a cooler surface temperature of about 3,500 to 3,600 Kelvin. KY Canis Majoris is often cited in discussions of the largest stars because its radius may extend beyond that of KY Cygni, but measurement challenges and variability make precise comparisons difficult. Nonetheless, both stars illustrate the extreme end of stellar evolution, where a combination of immense size and relatively cool temperatures creates luminous but diffuse giants. Then there's KY Cygni, another contender for one of the largest known stars. Located roughly 9,500 light-years away in the constellation Scutum, KY Cygni has an estimated radius of up to 1,700 times that of the Sun, which in some studies may surpass KY Cygni. It is a pulsating red supergiant, classified as a semi-regular variable star, meaning its size and brightness fluctuate over time. These pulsations affect measurements, creating some uncertainty about whether KY Cygni is truly the largest star in volume. Its surface temperature is slightly lower than KY Cygni's, around 3,300 to 3,400 Kelvin, and its immense size combined with cooler temperature gives it a deep, glowing red appearance. The variability and distant location of KY Cygni make it an elusive target for detailed study, much like KY Cygni, yet both stars provide critical insights into the late evolutionary stages of massive stars. When we put KY Cygni in the context of these giants, several patterns emerge. First, all four stars, KY Cygni, Betelgeuse, KY Canis Majoris, and KY Cygni, share similar surface temperatures, hovering around 3,300 to 3,600 Kelvin. This cool temperature is characteristic of red supergiants and red hypergiants, whose enormous size has spread their energy over a vast surface, cooling the outer layers relative to smaller stars. Second, all exhibit enormous radii, ranging from nearly 1,000 times the Sun's radius to possibly over 1,700 times. The differences in size are striking in terms of solar system scale, but in cosmic terms, these stars all occupy the extreme upper limit of known stellar dimensions. A third point of comparison is luminosity versus visibility. Betelgeuse, despite being smaller than KY Cygni, is much more prominent in our night sky due to its relative closeness. KY Cygni, while extremely luminous, is far more distant, making it invisible without advanced telescopes. KY Canis Majoris and KY Cygni, on the other hand, are both distant and enshrouded in dust, which complicates direct observation. These factors illustrate an important lesson. Apparent brightness is not the same as intrinsic luminosity, and even enormous stars can appear faint from Earth depending on distance and intervening cosmic material. The comparison also highlights differences in atmospheric structure and stability. Stars like VY Canis Majoris and KY Cygni have extremely extended atmospheres, with layers of gas reaching far into space. These atmospheres are turbulent, with massive convection currents and pulsations that contribute to mass loss. Betelgeuse and KY Cygni share these characteristics, although the scale and intensity vary. The extended atmospheres are critical to understanding how these stars shed material, enriching the surrounding interstellar medium and ultimately affecting the life cycle of future stars. Another interesting aspect is variability. Both KY Cygni and KY Cygni are semi-regular variable stars, meaning their brightness and size fluctuate over time. These pulsations are caused by complex interactions between radiation pressure, gravity, and convective currents in the outer layers. Betelgeuse, too, exhibits variability, sometimes dimming noticeably over months or years, as was spectacularly observed in late 2019, early 2020. VY Canis Majoris, while less regular in its variability, also experiences episodic mass ejections and brightness changes. Comparing KY Cygni to these giants allows astronomers to see patterns and differences in the late stages of stellar evolution, providing a more complete picture of how supergiants behave. It's also worth noting mass versus volume distinctions. While KY Cygni's radius is immense, its mass is not proportionally enormous. It likely ranges around 25 to 30 solar masses, similar to or slightly less than some of these other giants. VY Canis Majoris, for example, may have a mass slightly higher, though uncertainties in measurement remain. This disparity between mass and volume explains why these stars have such low densities. Imagine a star with billions of times the Sun's volume but only a few dozen times its mass. Its outer layers are incredibly diffuse, almost balloon-like, giving rise to the extended, ghostly atmospheres that define these cosmic leviathans. In summary, KY Cygni is remarkable but not alone. It shares characteristics with other massive stars: cool temperatures, immense radii, extended atmospheres, and variability, but it occupies a unique niche in the cosmic hierarchy. Depending on the measurement method, it rivals or slightly exceeds Betelgeuse and approaches the scale of KY Cygni and VY Canis Majoris. Together, these giants illustrate the upper limits of stellar evolution, the extremes of size, and the astonishing diversity among the largest stars in the universe. KY Cygni, in particular, offers a compelling blend of extreme size, distance, and relative obscurity, making it a perfect subject for exploring the outer bounds of stellar physics. As we examine KY Cygni and its colossal cousins, it becomes clear that these stars are not just curiosities, they are laboratories of extreme physics, offering insights into how matter behaves under conditions that would crush smaller stars. And this naturally brings us to the next key facet of KY Cygni's story: its life stage. Understanding where it is in its stellar life cycle reveals not just how it became so enormous, but also what the future may hold for this cosmic titan. Having explored KY Cygni in the context of other cosmic giants, we now turn to a critical question: what stage of life is this star in? Understanding KY Cygni's life stage provides not only context for its enormous size and relatively cool temperature, but also clues about its future, its stability, and its ultimate fate. KY Cygni, like other red supergiants, is a star in the late stage of stellar evolution, a phase marked by instability, rapid changes, and a ticking cosmic clock counting down toward the star's explosive demise. KY Cygni is classified as a red supergiant, a type of star that represents the final evolutionary stage of massive stars, typically those that begin life with 10 to 40 times the mass of our Sun. These stars spend millions of years fusing hydrogen into helium in their cores, a period known as the main sequence, which is the longest and most stable phase of a star's life. For comparison, our Sun is about 4.6 billion years old and is roughly halfway through its main sequence phase, expected to remain stable for another 5 billion years or so. KY Cygni, however, has long since left this main sequence phase, having exhausted the hydrogen in its core. This is the beginning of its journey into stellar senescence, a transformation that turns it into a vast, red supergiant. The transition to a red supergiant occurs when the core of a massive star can no longer sustain hydrogen fusion at the rate necessary to balance the inward pull of gravity. As hydrogen fusion ceases, the core contracts under its own weight, heating up as it does so. At the same time, the outer layers of the star expand dramatically, sometimes to over 1,000 times the Sun's radius, as in KY Cygni's case. This expansion causes the surface to cool, which is why red supergiants like KY Cygni glow with their characteristic deep red hue rather than the white or blue light of hotter, smaller stars. During this late stage, KY Cygni is undergoing complex nuclear reactions in its core. While the hydrogen is depleted, helium fusion begins, producing carbon and oxygen. As the core evolves further, it can burn progressively heavier elements. Carbon fuses into neon, neon into oxygen, and oxygen into silicon. Each stage occurs more rapidly than the last. For a star of KY Cygni's mass, the final silicon burning phase lasts only days to weeks. This is a stark contrast to its millions of years on the main sequence and highlights just how ephemeral and dramatic the red supergiant phase is. The expansion into a red supergiant also makes the star highly unstable. The outer layers are diffuse and extended, creating enormous convection cells that can dwarf planets. These layers are prone to pulsations, mass ejections, and surface irregularities, which are often observed as semi-regular variability in brightness. KY Cygni's instability is a hallmark of its advanced age and indicates that the star is nearing the final chapters of its stellar life. Its enormous size and turbulent outer layers are both a consequence and a symptom of the tremendous pressures and energies at work inside. Another key characteristic of this late life stage is the rapid consumption of nuclear fuel. Whereas main sequence stars like the Sun burn their hydrogen slowly over billions of years, red supergiants like KY Cygni burn helium and heavier elements at an accelerated rate. The higher core temperatures and pressures allow fusion of heavier elements, but this process consumes fuel exponentially faster. This is why KY Cygni's remaining lifespan as a red supergiant is relatively short in cosmic terms, a few 100,000 years at most, a mere instant compared to the Sun's multi-billion-year main sequence lifespan. The red supergiant phase is brief but spectacular, characterized by enormous energy output, enormous size, and instability that makes the star a ticking time bomb in stellar terms. The life stage of KY Cygni also explains many of its observable properties. Its low surface temperature, immense radius, and variable brightness are all direct consequences of being a late-stage red supergiant. The extended atmosphere, with layers of gas stretching millions of kilometers into space, forms because the star's gravity cannot hold onto the outermost material against the outward pressure of radiation and convection. The star is literally shedding parts of itself as it swells to extreme dimensions. This mass loss contributes to the surrounding interstellar medium, enriching the galaxy with elements that will later form new stars, planets, and even the building blocks of life. In addition, KY Cygni's stage in life provides insight into what lies ahead for massive stars. Red supergiants do not linger indefinitely. Once the core accumulates enough iron through successive nuclear fusion stages, it can no longer generate energy through fusion. Iron is inert in terms of energy production, so the balance between radiation pressure and gravity collapses catastrophically. This core collapse leads to a supernova explosion, the star's ultimate finale. For KY Cygni, being a red supergiant in this advanced evolutionary stage means that, while the explosion may be tens or hundreds of thousands of years away, it is inevitable. The star has already entered the final chapter of its life, a phase defined by expansion, instability, and preparation for the dramatic endgame. It's also worth noting that not all red supergiants survive to explode as supernovae in the same way. The exact outcome depends on mass, rotation, and composition. KY Cygni, with its massive size and extended atmosphere, is a textbook candidate for a core collapse supernova, likely leaving behind a neutron star or, if its core is sufficiently massive, a black hole. Its life stage is a critical window for astronomers to study the processes that lead to supernovae, providing a glimpse into phenomena that shape the cosmos. Finally, this life stage makes KY Cygni a laboratory for understanding stellar evolution. Its size, instability, and advanced nuclear processes allow scientists to test models of how stars live and die, how they shed material, and how they enrich the interstellar medium with heavy elements. Red supergiants like KY Cygni are fleeting in cosmic terms, but they are essential to the story of the universe, linking the life of stars to the evolution of galaxies and planetary systems. In summary, KY Cygni is far beyond the calm, long-lived main sequence stage of stars like the Sun. It is a red supergiant in the twilight of its life, massive, bloated, turbulent, and burning fuel at a furious pace. Its enormous radius, cooler surface, and variable brightness are all signs of this late-stage evolution. Understanding its current life stage allows us to anticipate its future, to model the physical processes at work inside it, and to appreciate the extraordinary extremes that stars can reach as they approach the end of their lifespans. And as we consider this advanced life stage, the next natural question arises. How exactly does KY Cygni burn through its nuclear fuel, and what makes this consumption so rapid compared to smaller stars like our Sun? That brings us to the critical topic of fuel consumption, a window into the intense inner workings of this cosmic giant. Having established that KY Cygni is a red supergiant in the late stage of stellar evolution, we now turn to one of the most dramatic and defining aspects of its existence: fuel consumption. The story of KY Cygni's nuclear fuel is, in many ways, a story of urgency and intensity. Unlike smaller, stable stars such as our Sun, which can burn steadily for billions of years, KY Cygni is racing through its remaining fuel at a staggering pace. Understanding this rapid consumption not only explains the star's short remaining lifespan but also sheds light on the extreme physics driving its immense size, instability, and eventual fate. Stars shine by converting matter into energy through nuclear fusion in their cores. For stars like our Sun, this process primarily fuses hydrogen atoms into helium. The Sun is relatively small and stable, so it burns its hydrogen slowly, producing a steady, consistent output that allows it to last for roughly 10 billion years in the main sequence phase. This slow consumption is a function of mass. Smaller stars exert less pressure on their cores, resulting in lower temperatures and a slower fusion rate. Essentially, the Sun can afford to burn its fuel leisurely over billions of years. KY Cygni, however, is a massive star, estimated to be roughly 25 to 30 times the Sun's mass. Greater mass creates enormous pressure and heat in the star's core, dramatically accelerating nuclear reactions. While the Sun fuses hydrogen at a moderate pace, KY Cygni's core pressure has long since surpassed the main sequence threshold, leading to fusion of heavier elements. After exhausting hydrogen, KY Cygni has moved on to helium fusion, producing carbon and oxygen, and may now be fusing even heavier elements like neon, magnesium, and silicon. Each successive stage of fusion requires higher temperatures, which in turn increases the rate of energy production and the rate at which fuel is consumed. The result is a cosmic sprint. While the Sun will continue burning hydrogen for billions of years, KY Cygni may have only a few 100,000 years, or even less, before its nuclear fuel is exhausted. To put this in perspective, if the Sun's remaining hydrogen-burning lifespan was scaled down to the length of a human lifetime, KY Cygni's remaining lifespan would be measured in mere hours or days. Its enormous size and rapid consumption make it one of the most energetically voracious stars in the galaxy. This rapid fuel consumption also explains the instability and turbulence in KY Cygni's outer layers. As the core burns heavier elements at breakneck speed, energy floods outward, pushing against gravity and causing the outer envelope of the star to expand and convect. These convection currents are enormous, billions of kilometers across, and create pulsations that manifest as changes in brightness. In fact, KY Cygni's classification as a semi-regular variable star is a direct consequence of this internal instability, which is itself tied to the rapid pace of nuclear fusion. Each heartbeat of the star's brightness reflects the turbulent energy transfer from core to surface. Another aspect of fuel consumption in red supergiants like KY Cygni is mass loss. As nuclear fusion ramps up in the core, radiation pressure and convective motions in the outer layers push stellar material into space. KY Cygni sheds gas and dust at an extraordinary rate, losing a fraction of its mass every million years. While this may sound slow by human standards, in cosmic terms it is extremely fast. This ejected material contributes to the interstellar medium, enriching the galaxy with elements heavier than hydrogen and helium, elements that will eventually form new stars, planets, and even the building blocks of life. In this sense, KY Cygni's rapid fuel consumption is intimately linked to its role as a cosmic recycler, accelerating the cycle of matter in the galaxy. It's also worth noting the contrast between burning efficiency and size. While KY Cygni is enormous and its outer layers vast and diffuse, the real engine of destruction is the core. The fusion rate in the core is staggering compared to smaller stars, producing energy that the star cannot contain without expanding outward. The cooler, swollen outer layers are effectively a byproduct of this rapid energy generation. In other words, the star's massive radius and extended atmosphere are signs of a star desperately trying to maintain equilibrium while its core races through fuel at a breakneck pace. This rapid consumption has a profound implication for the future of KY Cygni. Stars that burn quickly do not have time to settle into stability, and the faster a star consumes its fuel, the shorter its life becomes. The accelerated fusion of heavier elements means that KY Cygni is moving inexorably toward the core collapse phase, where fusion will no longer be able to support the core against gravity. In the span of a few thousand years, or possibly even less, KY Cygni will reach the point where iron has accumulated in the core. Iron cannot release energy through fusion, so the balance between outward pressure and gravitational pull collapses catastrophically. This leads naturally into the possible fate of KY Cygni. Because of its rapid fuel consumption and massive core, the star is expected to end its life in a supernova explosion. At the moment, the star continues to burn through its fuel, expanding, pulsating, and shedding mass, but each day brings it closer to a dramatic finale. The pace of fuel consumption is not just a scientific curiosity, it is the ticking clock of a cosmic giant, counting down to a spectacular event that will shape the surrounding galaxy. In comparison to our Sun, KY Cygni's energy output is like a fire hose to the Sun's garden sprinkler. It consumes fuel so quickly that its life, though intense and luminous, is extremely brief on the cosmic timescale. And this rapid consumption is intimately tied to every other property we have discussed: its enormous radius, cool surface temperature, semi-regular variability, and massive atmosphere. Each is a consequence of the same underlying cause. KY Cygni's core is burning furiously, and the outer layers are responding to that intense energy flow. In summary, KY Cygni's fuel consumption is extraordinary. While smaller stars like the Sun burn slowly and steadily, KY Cygni is consuming hydrogen, helium, and heavier elements at a pace that will leave it near exhaustion in only a fraction of the Sun's lifespan. Its size, instability, pulsations, and mass loss are all direct consequences of this rapid consumption. And ultimately, this frantic pace sets the stage for one of the most dramatic events in the universe: the supernova explosion that will mark the star's death. The natural next question, then, is what will happen when KY Cygni reaches that end stage? Its rapid fuel consumption leads inevitably to a cataclysmic finale, and the possible fate of the star, whether it leaves behind a neutron star, a black hole, or something else, offers a glimpse into the violent life cycle of massive stars and their role in the cosmos. Having examined KY Cygni's rapid fuel consumption, we now turn to the inevitable climax of its stellar life, its possible fate. Every massive star eventually reaches a point where nuclear fusion can no longer sustain the outward pressure needed to counteract gravity, and KY Cygni is no exception. The physics that govern this process are both fascinating and catastrophic, illustrating the extreme and violent dynamics that mark the final stages of a red supergiant's life. KY Cygni's journey toward its ultimate fate begins with its core. After millions of years of fusion, the star has successively burned hydrogen, helium, carbon, neon, oxygen, and silicon in its core. Each stage produces heavier elements and occurs more rapidly than the last. Eventually, this process leads to the production of iron. Iron fusion is energetically unproductive. It does not release energy but instead absorbs it, which halts the outward pressure that has been holding the star's core in equilibrium. At this critical moment, gravity overwhelms the core's support, triggering a catastrophic collapse. The result is a core collapse supernova, one of the most energetic events in the universe. During this process, the core implodes within seconds, reaching densities comparable to an atomic nucleus. The outer layers of the star, previously held in check by radiation pressure and thermal expansion, are suddenly expelled outward at tremendous velocities, often exceeding 10% of the speed of light. This explosion can briefly outshine an entire galaxy, releasing as much energy in a few days as the Sun will produce over its entire 10 billion-year lifespan. For KY Cygni, this supernova would be a spectacular and violent display, scattering vast amounts of matter and energy into the surrounding interstellar medium. After the explosion, the fate of the collapsed core depends on its mass. If the remnant is between roughly 1.4 and 3 solar masses, the Chandrasekhar and Tolman-Oppenheimer Volkoff limits, it stabilizes as a neutron star, an incredibly dense object made almost entirely of neutrons. Neutron stars are typically only about 20 kilometers, 12 miles, in diameter. Yet they contain more mass than the Sun. The density is so extreme that a single teaspoon of neutron star material would weigh billions of tons. If the remnant is more massive than approximately 3 solar masses, gravity continues to dominate, compressing the core into a black hole, a region of space where gravity is so strong that not even light can escape. Given KY Cygni's estimated initial mass of 25 to 30 solar masses, astronomers generally predict that it could leave behind either a neutron star or a black hole, depending on how much mass is lost during its red supergiant phase and the dynamics of the supernova explosion. Mass loss prior to the explosion, through stellar winds and ejected gas, plays a crucial role. If KY Cygni loses sufficient mass before core collapse, the remnant may fall into the neutron star category. Otherwise, a black hole is the more likely outcome. Either result represents a dramatic transformation from the bloated, diffuse red supergiant to a compact, extreme object. Another fascinating aspect of this supernova scenario is the impact on the surrounding environment. When KY Cygni explodes, it will eject enormous amounts of heavy elements, carbon, oxygen, silicon, iron, into space. These elements are the building blocks for new stars, planets, and even life. In this sense, KY Cygni's death is not just an end but also a beginning. It enriches the galactic ecosystem, seeding future generations of celestial objects with the products of its nuclear fusion. Supernovae like this are essential to cosmic evolution, linking the death of one star to the creation of others. It's worth noting that while the explosion would be extraordinarily luminous, KY Cygni is far enough away, roughly 5,000 light-years, that it would pose no danger to Earth. The radiation would reach us as a spectacular light show in the sky, and if visible to the naked eye, it could briefly rival the Moon in apparent brightness. Neutrinos from the core collapse would pass harmlessly through our planet, while the ejected gas and dust would continue to disperse across space, taking thousands of years to affect nearby star-forming regions. In other words, this cosmic event would be awe-inspiring but safe from any catastrophic impact on life on Earth. Astronomers are intensely interested in stars like KY Cygni precisely because they offer a preview of such cataclysmic endings. Observing red supergiants gives insight into the final stages of massive stellar evolution and the physics of supernovae. For example, by monitoring pulsations, mass loss, and brightness variations, scientists can better predict how the star's core is evolving and how close it may be to collapse. While we cannot predict the exact moment KY Cygni will explode, its current characteristics indicate that it is in the advanced pre-supernova stage, a ticking cosmic clock. The possible fate of KY Cygni also underscores the cycle of stellar life. From its formation in a dense molecular cloud millions of years ago to its current bloated red supergiant state, the star has undergone successive phases of nuclear fusion. Its impending supernova will mark the dramatic conclusion of its life, but the materials it disperses will eventually coalesce into new stars, planets, and potentially life-bearing systems. In this sense, KY Cygni's death is an integral part of the ongoing evolution of the galaxy. In summary, KY Cygni's possible fate is both spectacular and inevitable. As a red supergiant, it is consuming its nuclear fuel at an extraordinary rate, and once its core accumulates too much iron, gravitational collapse will trigger a supernova explosion. The core may stabilize as a neutron star or continue collapsing into a black hole, while the ejected material enriches the galaxy with heavy elements. The explosion itself would be an awe-inspiring event, visible across vast distances but safely far from Earth, and it serves as a reminder of the extremes of stellar evolution and the impermanence of even the largest stars. The next natural topic is the impact of the supernova, exploring what the consequences of such a stellar explosion would be for its surroundings and the wider galaxy, and why it remains a safe yet astonishing phenomenon from our perspective on Earth. The possible fate of KY Cygni, as we've seen, is almost certainly a supernova explosion, one of the most violent and spectacular phenomena in the universe. But what would this mean for the galaxy around it, and for us here on Earth? The impact of a supernova is immense, reshaping its cosmic neighborhood and leaving behind remnants that echo across the galaxy for millennia. Yet, while the explosion of KY Cygni will unleash titanic forces, the star's distance of roughly 5,000 light-years ensures that we can admire the event as a cosmic spectacle without any real danger to our planet. When KY Cygni finally reaches the end of its life and its core collapses, the explosion will release an almost unimaginable amount of energy. In the span of seconds, it will radiate as much energy as our Sun will emit over its entire 10 billion-year lifetime. This burst will produce a brilliant flash of light that could outshine the combined brightness of all the stars in the Milky Way for several days or weeks. From Earth, the event would likely be visible even during the day, rivaling the brightness of the Moon in the night sky. Imagine stepping outside and seeing a new, red-tinged star that suddenly dominates the heavens, an awe-inspiring reminder of the raw power of the cosmos. But while the light show would be extraordinary, the radiation and energy released pose no direct threat to Earth. At a distance of 5,000 light-years, the dangerous forms of radiation, gamma rays, high-energy particles, and neutrino bursts, would dissipate long before reaching us. For context, astrophysicists generally consider supernovae within 30 to 50 light-years to be potentially hazardous to Earth's biosphere. At 5,000 light-years, KY Cygni supernova is more than 100 times farther away than that danger zone. The neutrinos would stream harmlessly through our planet, undetected except by specialized instruments, while the electromagnetic radiation would arrive as nothing more than a glorious spectacle in the sky. For the regions of space closer to KY Cygni, however, the consequences would be transformative. The explosion would obliterate the star's outer layers, ejecting them into the interstellar medium at speeds of thousands of kilometers per second. This expanding shockwave would plow into the surrounding gas and dust, heating it, compressing it, and triggering new waves of star formation. Astronomers call this process supernova feedback, and it is one of the key ways galaxies recycle material. Without such explosions, the galaxy would lack many of the heavy elements, like carbon, oxygen, silicon, and iron, that are essential for forming planets and life. In this sense, KY Cygni's death is not just an end, but also a gift to the galaxy, enriching its surroundings with the elements forged in its core. The supernova's remnants would persist for thousands, even tens of thousands of years. Expanding shells of glowing gas would form what astronomers call a supernova remnant, visible in radio, optical, and X-ray wavelengths. These remnants are some of the most beautiful structures in the universe, intricate webs of glowing filaments stretching across light-years of space. If KY Cygni explodes, its remnant will someday be catalogued and studied much like famous ones such as the Crab Nebula, offering future generations of astronomers a natural laboratory for understanding shockwaves, cosmic rays, and stellar death. In addition to enriching the galaxy with. Adding to the challenge is interstellar dust. The Milky Way is filled with clouds of gas and dust that scatter and absorb light, particularly in the visible spectrum. KY Cygni's light must travel through these clouds for 5,000 years before reaching Earth, and along the way, it is partially dimmed and reddened. This extinction makes it difficult to determine the star's true luminosity, color, and size. Observations in the infrared spectrum help bypass some of this dust, as infrared light can penetrate dusty regions more effectively. But even then, astronomers must carefully correct for dust effects. Variations in the amount and composition of interstellar dust along the line of sight introduce further uncertainties, making precise measurements an ongoing challenge. Another major difficulty arises from KY Cygni's intrinsic variability. As a semi-regular variable star, KY Cygni's brightness changes over time due to pulsations in its outer layers. These pulsations cause the star to expand and contract, slightly altering its radius and luminosity over periods ranging from months to years. Because the star is constantly in motion, taking a single measurement of its size or brightness can be misleading. Astronomers must observe KY Cygni over long periods and track its variations to develop an accurate picture, and even then, the numbers represent averages or ranges rather than a precise value. This variability is both a complication and an opportunity, as it provides insights into the physical processes occurring in the outer layers of red supergiants. KY Cygni's extended atmosphere further complicates size measurements. Unlike compact stars, red supergiants do not have a sharply defined edge. Their outer layers are extremely diffuse, gradually thinning into space. Deciding where the surface of the star begins is partly a matter of definition. Some astronomers measure the radius based on where the optical depth reaches a certain value, while others use infrared or radio observations to trace the extended envelope of gas. Depending on the method, the estimated radius of KY Cygni can vary significantly, from roughly 1,300 to 1,400 times the Sun's radius, or even slightly higher. These variations are not contradictions but reflections of the star's complex, extended structure. Additionally, KY Cygni's shedding of material adds a dynamic layer to the problem. Red supergiants lose mass through stellar winds, ejecting gas and dust into space. Observations sometimes detect this expelled material surrounding the star, making it difficult to distinguish between the star itself and its surrounding envelope. The presence of this circumstellar material affects measurements of luminosity and radius because the star appears larger and brighter at certain wavelengths than it actually is. Untangling the star's true properties from the effects of its extended atmosphere and surrounding dust is a meticulous and ongoing task for astronomers. Instrumental limitations also play a role. While modern telescopes, such as Hubble, the Very Large Telescope, VLT, and infrared observatories, provide incredible resolution, KY Cygni is still essentially a point source in many observations due to its distance. Interferometric techniques, where multiple telescopes work together to create a virtual telescope with a much larger effective aperture, have been used to resolve the surfaces of red supergiants, including KY Cygni, but these methods are highly sensitive to atmospheric interference, calibration errors, and assumptions about the star's shape. Even with the best technology, there is a degree of estimation involved. Finally, KY Cygni's comparison with other stars also complicates the picture. When astronomers try to place it within a hierarchy of supergiants, uncertainties in measurements propagate. Small differences in the assumed distance or corrections for dust can change whether KY Cygni appears slightly larger than Betelgeuse or comparable to UY Scuti. This is why discussions of the largest star in the universe often include ranges or qualifiers. The extreme size of KY Cygni is beyond doubt, but the exact figure remains elusive. In summary, measuring KY Cygni is a challenging endeavor because of three intertwined factors: its great distance, the obscuring interstellar dust, and its intrinsic variability and extended atmosphere. Add to this the complications of mass loss and instrumental limitations, and we see why astronomers often report a range of values rather than a single number. These challenges do not diminish the significance of KY Cygni. They highlight the extreme conditions under which this star exists and the ingenuity required to study it from across the galaxy. Despite these difficulties, astronomers continue to make progress. Advances in infrared and radio observations, combined with long-term monitoring of variable stars, are refining our understanding of KY Cygni. Each new observation sheds light not only on its size but also on the physical processes that govern red supergiants, from convection and pulsation to mass loss and supernova precursors. The uncertainty, in a sense, makes KY Cygni all the more fascinating. It is a living laboratory of extreme stellar physics, offering mysteries that push the limits of observation and theory alike. The natural continuation from here is to explore KY Cygni's variable star nature in more detail, how these pulsations and fluctuations manifest, and what they reveal about the dynamic processes occurring within this immense red supergiant. Building on the challenges of measuring KY Cygni, one key factor contributing to that uncertainty is its variable nature. KY Cygni is classified as a semi-regular variable star, a designation that reveals much about the dynamic and constantly evolving processes occurring within this colossal red supergiant. Unlike stars with steady output, semi-regular variable stars experience periodic or quasi-periodic fluctuations in brightness, driven by pulsations in their outer layers, mass loss, and internal convective activity. These variations add a fascinating, almost living quality to KY Cygni, demonstrating that even stars of unimaginable size are not static objects but dynamic, evolving systems. The semi-regular variability of KY Cygni arises primarily from radial pulsations. In simple terms, the star's outer envelope expands and contracts over time. This pulsation is a result of the delicate interplay between gravity pulling inward and radiation pressure pushing outward. As KY Cygni's outer layers expand, the surface cools slightly and its apparent brightness diminishes. When the layers contract, the surface heats up and the star appears brighter. These cycles are not strictly periodic, as they can be influenced by internal turbulence, convection, and stochastic processes in the star's massive envelope. The result is a quasi-regular pattern of brightening and dimming that can last for hundreds of days or even longer between peaks and troughs. Observationally, these brightness variations are measurable but subtle from Earth. KY Cygni's apparent magnitude fluctuates in ways that can be detected with sensitive photometric instruments, but because it is distant and partially obscured by interstellar dust, the variations are somewhat muted compared to nearer variable stars like Betelgeuse. Long-term monitoring has revealed that KY Cygni does not follow a single, consistent cycle. Instead, multiple overlapping pulsation modes occur, reflecting the complex internal structure of the star. Some pulsations correspond to the overall expansion and contraction of the entire star, while others arise from local convection cells and turbulent flows near the surface. The semi-regular variability also influences other observed properties of KY Cygni. For example, when the star's radius expands during a pulsation, the outer layers become more tenuous, allowing more mass to escape via stellar winds. Conversely, during contraction, the outer layers are denser and less material is lost. These fluctuations directly affect the mass loss rate, which is already significant in red supergiants and contributes to their extended atmospheres and surrounding envelopes of gas and dust. Essentially, the star's variable nature is not just a superficial change in brightness, it is a visible manifestation of the underlying dynamic processes shaping its evolution. Moreover, the pulsations have implications for infrared and radio observations. Since KY Cygni's outer layers periodically swell, the star appears slightly larger at certain wavelengths during expansion phases. This effect complicates precise measurements of its radius, reinforcing the challenge we discussed in the previous segment. Variability can also affect estimates of luminosity, as brightness changes translate into energy output fluctuations over time. By carefully monitoring these variations, astronomers can gain valuable insights into the internal structure and convective behavior of KY Cygni, which is otherwise hidden from direct observation. Semi-regular variability is not unique to KY Cygni. It is common among red supergiants and asymptotic giant branch stars. However, KY Cygni's extreme size, mass, and luminosity make its pulsations particularly dramatic. The star's immense radius means that even small relative expansions or contractions translate into enormous absolute changes in volume and surface area. The energy involved in driving these pulsations is staggering, and studying them provides a rare glimpse into the physics of extreme stellar envelopes, where convection, radiation pressure, and gravity interact in ways that defy terrestrial intuition. Interestingly, semi-regular variability can also serve as a predictive tool. By tracking KY Cygni's pulsations over time, astronomers can estimate changes in its radius, surface temperature, and mass loss rate, which in turn inform models of its eventual supernova explosion. Understanding the star's variable behavior helps scientists anticipate how the outer layers will respond as the core approaches collapse, offering crucial data for simulations of red supergiant supernovae. The pulsations are not just a curiosity, they are an observable clue to the star's imminent evolution. Finally, the variable nature of KY Cygni adds to its cosmic mystique. To the casual observer, the star may appear as a faint red point of light, barely distinguishable from its surroundings. But for astronomers monitoring it over months and years, KY Cygni is alive with motion, breathing in a slow, rhythmic cycle of expansion and contraction. This variability, combined with its enormous size and extended atmosphere, makes the star a living laboratory for understanding stellar physics at extremes, offering a dynamic perspective on how massive stars behave in their final stages. In summary, KY Cygni's classification as a semi-regular variable star is a key aspect of its identity. Its brightness fluctuates over time due to radial pulsations and convective processes in its enormous outer layers. These variations affect its radius, mass loss rate, and observed luminosity, and they provide astronomers with vital information about the star's internal dynamics and future evolution. The pulsations remind us that KY Cygni is not a static, eternal object. It is a living, breathing, evolving giant, moving toward its ultimate fate in a slow, dramatic rhythm that spans decades and centuries. From understanding its variability, we naturally transition into another defining feature of KY Cygni: its massive, extended atmosphere. The outer layers of this red supergiant are not compact like the Sun's. Instead, they stretch millions of kilometers into space, influencing the star's behavior, its interaction with surrounding material, and the environment that will eventually be shaped by its supernova. Building on KY Cygni's variable nature, we now turn to one of the most striking features of this red supergiant: its massive, extended atmosphere. Unlike smaller stars, whose outer layers are relatively compact and well-defined. KY Cygni's outer envelope is immense, tenuous, and layered, stretching millions of kilometers into space. This extended atmosphere is both a consequence of the star's enormous size and a driver of its behavior, influencing variability, mass loss, and even the environment surrounding the star. Understanding this feature is crucial for appreciating how red supergiants live and die on a scale almost impossible to imagine. KY Cygni's atmosphere can be thought of as a series of nested, diffuse layers. Its visible surface, the photosphere, is only the innermost layer of a much larger envelope of gas. Beyond this photosphere, there are cooler, rarefied layers of hydrogen, helium, and heavier elements that extend outward, gradually merging into the surrounding interstellar medium. Unlike planets or smaller stars, KY Cygni does not have a sharp edge. Its atmosphere thins slowly, giving the star a fuzzy boundary that can make it difficult to measure the exact radius. Observations in the infrared and radio wavelengths reveal that the star's atmosphere can extend far beyond what is visible in optical light, encompassing regions hundreds of millions of kilometers from the core. One reason for this extreme extension is the balance between gravity and radiation pressure. KY Cygni's immense core generates prodigious amounts of energy, which pushes outward against the gravitational pull trying to compress the star. In the outer layers, gravity is weaker relative to the outward pressure, allowing the gas to expand dramatically. These expanded layers are extremely low in density, sometimes millions of times more diffuse than air on Earth, yet they constitute a massive volume. Despite their tenuousness, these layers play a critical role in the star's energy transport, pulsation, and mass loss processes. The dynamic nature of the atmosphere further amplifies its scale. Radial pulsations and convective flows cause the outer layers to move constantly, rising and falling over periods of months or years. These motions create shocks and turbulence that can lift material away from the star entirely. In KY Cygni, the extended atmosphere interacts with stellar winds, carrying gas and dust into space. This interaction contributes to the creation of a circumstellar envelope, a halo of material surrounding the star, which can be observed in infrared light. In essence, KY Cygni's atmosphere is not static. It is a roiling, shifting ocean of gas responding to the forces of gravity, radiation, and internal convection. The extended atmosphere also influences the star's observed properties. As the star pulsates, its outer layers expand and contract, altering its radius and surface temperature. During expansion, the photosphere appears cooler and the star dims slightly. During contraction, the photosphere heats up and the star brightens. Because the outer layers are so diffuse, these changes are magnified. Even a small pulsation can move millions of kilometers of gas, affecting how we perceive the star from Earth. This explains part of the variability discussed in the previous segment and highlights the intimate link between KY Cygni's atmosphere and its observable behavior. Another fascinating aspect of the extended atmosphere is its role in chemical enrichment. As the outer layers are lifted away by stellar winds or expelled during pulsations, they carry with them elements formed in the star's core, such as carbon, nitrogen, and oxygen. This process slowly enriches the surrounding interstellar medium, seeding the galaxy with material that can eventually form new stars, planets, and even the raw ingredients for life. The massive atmosphere is effectively a conduit for the star to contribute to the galactic ecosystem long before its supernova. The extended atmosphere also complicates observational measurements. Because there is no sharply defined edge, astronomers must define a radius based on where the optical depth reaches a certain level or where the emission at a particular wavelength diminishes. Different observational techniques yield slightly different sizes, contributing to the uncertainty we discussed in the previous segment. Interferometric imaging has allowed astronomers to map parts of the atmosphere, revealing convective cells, hotspots, and irregularities that would be impossible to see with conventional telescopes. These features give us a rare glimpse into the weather on the surface of a star many times larger than the Sun. Finally, the extended atmosphere is intimately connected to KY Cygni's eventual supernova. The outer layers, already diffuse and expanded, will be the first to be expelled when the core collapses, creating the spectacular explosion visible across the galaxy. The interaction of the supernova shockwave with this massive envelope will influence the shape, brightness, and composition of the resulting supernova remnant, leaving lasting traces in the surrounding space. In other words, KY Cygni's atmosphere is both a defining feature of its current state and a key player in the drama of its ultimate demise. In summary, KY Cygni's massive, extended atmosphere is a defining characteristic of this extraordinary red supergiant. Comprised of nested, diffuse layers of gas, it stretches millions of kilometers into space, influenced by gravity, radiation pressure, pulsation, and convection. It contributes to the star's variability, facilitates mass loss, enriches the surrounding interstellar medium, and sets the stage for the eventual supernova. The atmosphere turns KY Cygni into not just a star, but a dynamic system, an enormous, roiling entity whose effects extend far beyond its visible surface. From here, it is natural to transition to the next aspect of KY Cygni's story: the dust and gas it sheds into space, which is intimately tied to its extended atmosphere and has profound consequences for the galactic environment. Continuing from the massive atmosphere of KY Cygni, we now focus on one of its most important roles in the galactic ecosystem: the shedding of dust and gas into space. This process is both a natural consequence of its enormous, unstable outer layers and a critical mechanism by which stars like KY Cygni influence the broader cosmos. Far from being isolated, KY Cygni actively participates in the cycle of stellar birth and death, enriching its surroundings with heavy elements and seeding future generations of stars and planets. KY Cygni's stellar winds are a primary driver of material loss. These winds are generated by the interplay of radiation pressure from the star's intense energy output, the buoyancy of hot gas in its convective envelope, and pulsational expansion of the outer layers. The wind carries gas and dust outward at velocities of tens to hundreds of kilometers per second. Over thousands of years, these steady outflows can remove a significant fraction of the star's mass, creating a halo of circumstellar material that can extend for millions of kilometers beyond the visible surface. This is not a gentle process. The star continuously loses material in a way that reshapes both its immediate environment and the interstellar medium on a larger scale. In addition to steady winds, KY Cygni experiences episodic mass ejections. These are more violent, sporadic expulsions of gas and dust, often associated with the star's pulsations or surface instabilities. Giant convection cells, enormous regions of rising and sinking gas, can push material outward beyond the star's gravitational hold. The resulting clumps of matter can form shells, arcs, or filaments around the star, observable in infrared and radio wavelengths. In many ways, KY Cygni is constantly breathing material into space, a slow but steady recycling of matter that plays a vital role in galactic chemical evolution. The composition of the ejected material is particularly significant. Unlike lighter elements such as hydrogen and helium, the gas and dust expelled from red supergiants like KY Cygni contain heavier elements forged in the star's core, including carbon, oxygen, silicon, and nitrogen. These elements are essential for the formation of rocky planets, complex molecules, and ultimately the conditions for life. In essence, KY Cygni acts as a cosmic forge. The star produces heavy elements through nuclear fusion and then disperses them into space, where they can later coalesce into new stars, planetary systems, and organic chemistry. The expelled dust and gas also serve as seeds for new star formation. When the material mixes with the interstellar medium, it can accumulate in dense molecular clouds. Gravity pulls these clouds together, eventually leading to the collapse of regions dense enough to form new stars. In this way, KY Cygni is not just a passive object but an active participant in the ongoing cycle of stellar birth and death. Every particle shed from its outer layers has the potential to become part of a future solar system, a reminder that stars are intimately connected to the broader galactic ecosystem. Observations of KY Cygni's surroundings provide clear evidence of this process. Infrared telescopes reveal warm dust shells that glow as they absorb and re-emit the star's energy, while radio and submillimeter studies detect molecules and ions being carried outward by the stellar wind. These observations show that the material is not randomly dispersed. It forms structured envelopes and arcs shaped by the star's gravity, radiation, and pulsations. By mapping these structures, astronomers can estimate the mass loss rate, the density of the circumstellar environment, and even the chemical composition of the ejected material. Such data are invaluable for understanding how red supergiants influence the interstellar medium. The shedding of material also plays a role in preparing for the star's ultimate fate. As KY Cygni loses mass, the remaining core becomes more exposed, and the outer layers are less gravitationally bound. When the star eventually explodes as a supernova, the shockwave will interact with this circumstellar material, creating spectacular emission features and enhancing the brightness of the explosion. In some cases, the ejected gas can shape the resulting supernova remnant, producing intricate filaments and shells that can be observed long after the initial explosion. Thus, the dust and gas around KY Cygni are both a product of its current life and a precursor to its dramatic end. Another fascinating aspect is that this process connects KY Cygni to the broader galactic ecology. Without stars like KY Cygni shedding material, the galaxy would lack the heavy elements necessary to form planets and support chemical complexity. In a very real sense, KY Cygni and other red supergiants are cosmic gardeners, enriching the galactic soil so that future generations of stars and planetary systems can flourish. The cycle of stellar evolution is deeply intertwined. Stars are born from the remnants of older stars, live their lives, and then return enriched material to the cosmos, perpetuating a cycle that has continued for billions of years. In summary, KY Cygni's shedding of dust and gas is a remarkable and critical aspect of its existence. Driven by stellar winds, pulsations, and episodic mass ejections, this material enriches the surrounding interstellar medium with heavy elements, contributes to future star formation, and helps shape the environment into which the star will eventually explode. The extended atmosphere, pulsations, and mass loss all work together to make KY Cygni not just a massive star, but a dynamic contributor to the life cycle of the galaxy. This naturally leads us to the broader perspective. KY Cygni is part of a galactic ecosystem, influencing not just its immediate surroundings but the chemical evolution and star formation processes across its region of the Milky Way. Its role in the galaxy emphasizes the interconnectedness of stellar life cycles and the cosmic web in which stars, gas, and dust interact. Continuing from KY Cygni's shedding of dust and gas, we now examine its broader role in the galactic ecosystem. Stars like KY Cygni are far more than solitary celestial giants. They are active participants in the life of the galaxy. Through their creation of heavy elements, mass loss, and eventual explosive deaths, red supergiants play a critical role in galactic chemical evolution, star formation, and the cosmic recycling of matter. Without stars like KY Cygni, the Milky Way, and indeed the universe itself, would lack many of the elements essential for planets, organic chemistry, and the complexity of life. The enrichment process begins with nucleosynthesis, the fusion of lighter elements into heavier ones in the stellar core. During its life, KY Cygni converts hydrogen into helium, helium into carbon and oxygen, and eventually fuses progressively heavier elements such as neon, magnesium, silicon, and iron. These fusion reactions produce the bulk of the chemical elements heavier than hydrogen and helium. While smaller stars like the Sun also create some elements, red supergiants, due to their massive cores and high temperatures, are capable of synthesizing a far broader range of elements and in much greater quantities. KY Cygni is essentially a stellar factory, forging elements that cannot be produced in low-mass stars or in the primordial gas of the early universe. Much of this enrichment occurs before the star's final supernova. As KY Cygni sheds mass through its extended atmosphere, stellar winds, and episodic outbursts, it disperses elements such as carbon, oxygen, nitrogen, and silicon into the interstellar medium. These elements mix with surrounding gas clouds, creating metal-enriched regions where new stars and planetary systems can eventually form. In essence, KY Cygni is planting the seeds for the next generation of stars, embedding the products of its nuclear fusion into the raw material for future worlds. The culmination of KY Cygni's contribution comes with its supernova explosion, which dramatically enriches the galaxy with even heavier elements. During the core collapse supernova, elements like iron, nickel, and other rare metals are formed and violently ejected into space. The energy of the explosion drives these elements outward, dispersing them over vast regions of the interstellar medium. The supernova remnant becomes a repository of enriched material, often visible for thousands of years, and serves as the foundation for future star-forming regions. Without these supernovae, the galaxy would remain dominated by lighter elements, and planets with complex chemistry, including Earth-like planets capable of supporting life, would be far less likely to exist. Stars like KY Cygni also influence galactic dynamics. The energy injected into the interstellar medium by stellar winds and supernova shockwave stirs surrounding gas and dust, creating turbulence that can trigger or inhibit star formation. Dense molecular clouds can collapse under the influence of these shocks, forming clusters of new stars, while other regions may be dispersed, delaying star formation. In this way, KY Cygni's life and eventual death help regulate the rhythm of stellar birth across the galaxy, making it a critical actor in the Milky Way's ongoing evolution. The heavy elements released by KY Cygni also contribute to the formation of rocky planets and the chemistry of life. Elements such as carbon, oxygen, magnesium, and silicon, produced deep within its core and released through mass loss and supernova, eventually become incorporated into planetary systems. Iron, which is crucial for planetary cores and magnetic fields, is largely generated in massive stars and spread through supernovae. In a very real sense, KY Cygni and stars like it provide the raw materials for habitable worlds and the chemical foundations of biology. Every atom heavier than helium in our bodies was once inside a massive star like KY Cygni. Observations of other galaxies and supernova remnants show that red supergiants contribute disproportionately to the metallicity, the abundance of elements heavier than helium, in galactic regions. Their mass loss and explosive deaths create pockets of enriched gas that can be traced over millions of light-years. KY Cygni's own ejected material will eventually mix with the interstellar medium, helping to maintain the chemical diversity necessary for complex galactic ecosystems. In this sense, the star is both a destroyer and a creator. Its death fuels the birth of countless new stars, planets, and potentially even life-bearing environments. Another fascinating aspect of this role is timing. KY Cygni is currently in a phase of rapid fuel consumption and mass loss, meaning it is actively enriching its surroundings even before its final supernova. The combination of ongoing stellar winds and future explosive ejection ensures that the star's contribution to the galactic ecosystem is both continuous and cumulative. This ongoing enrichment is a reminder that red supergiants are dynamic participants in their cosmic neighborhoods, constantly shaping the material from which future generations of stars will form. In summary, KY Cygni exemplifies how massive stars serve as engines of galactic evolution. Through nucleosynthesis, mass loss, and supernova explosions, it produces and distributes heavy elements, seeds star-forming regions, and contributes to the chemical and dynamical processes that govern the Milky Way. Without stars like KY Cygni, the galaxy would lack much of the diversity of elements essential for planets, complex chemistry, and life itself. The star is a living testament to the interconnectedness of stellar life cycles and the cosmic web. Birth, evolution, and death are all part of an ongoing process of creation and renewal. As we consider KY Cygni's galactic impact, it is natural to reflect on how astronomers study it. Observations from advanced telescopes allow us to track its size, brightness, atmosphere, mass loss, and chemical contribution, helping scientists piece together the life story of this remarkable star. These observations provide not only scientific insight but also a window into some of the most extreme and fascinating physics in the universe. Astronomers' understanding of KY Cygni has been shaped through decades of careful observation, utilizing some of the most sophisticated telescopes and observatories available. Because it is a distant and heavily dust-obscured red supergiant, studying KY Cygni requires multi-wavelength observations, spanning optical, infrared, and radio regimes. Each of these observational approaches reveals a different aspect of the star, from its size and brightness fluctuations to the structure of its extended atmosphere and surrounding circumstellar material. Observing KY Cygni has not only provided insights into its individual properties but has also helped refine our understanding of the extreme physics governing red supergiants. Infrared observations have been particularly crucial because KY Cygni is heavily enshrouded by dust and gas, which absorb and scatter visible light. Infrared telescopes such as the Infrared Space Observatory, ISO, and ground-based facilities like the Very Large Telescope, VLT, in Chile have penetrated these dust layers, allowing astronomers to map the star's extended envelope and detect the presence of warm dust in its surroundings. By analyzing infrared emissions, scientists can determine the mass loss rate and study the composition of the dust, including silicates and other compounds formed in the star's outer layers. Infrared observations also help to measure the star's luminosity more accurately, correcting for the dimming effects of interstellar extinction. In addition, optical telescopes have been instrumental in studying KY Cygni's variability and spectral characteristics. Although much of its visible light is obscured, large aperture observatories such as the Hale Telescope at Palomar Observatory and the Keck Observatory have been used to obtain spectra, revealing the chemical composition of its atmosphere and the presence of molecular bands, including titanium oxide, TO, which is common in red supergiants. Spectroscopic analysis allows astronomers to measure surface temperatures, estimate the star's velocity, and track pulsations over time. These measurements, combined with photometric monitoring, help astronomers understand KY Cygni's semiregular variability and how it correlates with changes in the star's outer layers. Radio telescopes have provided another window into KY Cygni's behavior, particularly its mass loss processes. Facilities such as the Atacama Large Millimeter Submillimeter Array, ALMA, and the Very Large Array, VLA, have detected molecules and ions in the star's circumstellar envelope, including carbon monoxide, CO, which serves as a tracer for stellar winds and ejected gas. Radio observations allow astronomers to map the structure of the envelope, measure the velocity of outflowing material, and estimate the total mass being shed into space. These measurements are critical for understanding how KY Cygni contributes to the interstellar medium and for predicting the dynamics of the eventual supernova explosion. Interferometry has also been applied to KY Cygni, providing the highest resolution measurements of its apparent size and surface structure. By combining light from multiple telescopes, interferometers like the Very Large Telescope Interferometer, VLTI, have resolved the star's photosphere and even detected large convective cells on its surface. These observations reveal that KY Cygni's surface is not uniform but marked by giant rising and sinking bubbles of hot gas, which play a role in pulsations, variability, and mass ejection. The ability to image surface features on a star thousands of light-years away is a remarkable achievement, offering a glimpse into the complex processes driving the behavior of red supergiants. Space-based observatories such as the Hubble Space Telescope have contributed by providing high-resolution imaging of KY Cygni's environment. While Hubble cannot penetrate the densest dust layers in the optical, it has imaged surrounding nebulae and detected scattered light from circumstellar material. Combining these images with spectroscopic data allows astronomers to construct a more complete three-dimensional picture of the star's atmosphere and the material it is shedding. Space telescopes operating in other bands, such as the Spitzer Space Telescope in the infrared, have similarly contributed to mapping the thermal emission from dust grains, revealing the structure and extent of the star's envelope. Observations over decades have also highlighted KY Cygni's semiregular variability. Long-term monitoring programs, using both ground-based and space-based telescopes, have tracked fluctuations in brightness, correlating them with radial pulsations and atmospheric changes. These studies confirm that KY Cygni is not a static, unchanging object but a dynamic star with complex interactions between its core, outer layers, and extended envelope. Continuous observation allows astronomers to model these processes more accurately and to predict the star's behavior as it approaches the final stages of its life. Together, these telescopic observations have allowed astronomers to compile a remarkably detailed picture of KY Cygni despite its distance and obscuration. They reveal a star that is enormous, variable, and actively shedding mass, a star whose extended atmosphere and pulsations are linked to its ultimate fate, and a star whose chemical contributions and supernova potential have profound implications for the galaxy. Each wavelength, optical, infrared, radio, tells a different part of the story, demonstrating how multifaceted and interdependent modern astronomical techniques must be to study such extreme objects. In addition to its scientific significance, KY Cygni has captured the imagination of both professional astronomers and the public. Observations of its enormous size, its brilliant red hue, and the massive envelope of dust and gas surrounding it make KY Cygni a particularly vivid example of stellar extremes. Telescopic data allow not only for theoretical modeling but also for visualizations that communicate the staggering scale and beauty of such stars, reinforcing humanity's sense of wonder about the universe. In summary, KY Cygni has been studied with a range of sophisticated telescopes and observatories, including the VLT, ALMA, VLA, Hubble Space Telescope, Spitzer Space Telescope, and interferometric arrays. These instruments have revealed its size, variability, extended atmosphere, pulsations, and mass loss processes. They have also highlighted the chemical enrichment of its surrounding environment and provided a preview of the supernova to come. Observing KY Cygni demonstrates the power of combining multiple observational methods across the electromagnetic spectrum to understand one of the largest and most extreme stars in the galaxy. The fascination with KY Cygni naturally extends beyond telescopic study to why astronomers and the public alike find this star so captivating, not just for its physical extremes but for the mysteries it presents about stellar physics, evolution, and our place in the cosmos. KY Cygni captivates astronomers because it represents the extreme frontier of stellar physics, a natural laboratory for studying processes that cannot be replicated on Earth. Unlike average stars such as our Sun, KY Cygni challenges our understanding of stellar structure, evolution, and dynamics. Its enormous size, enormous mass loss rates, complex pulsations, and extended, turbulent atmosphere provide a unique opportunity to investigate the laws of physics under conditions of gravity, temperature, and pressure that are orders of magnitude beyond anything experienced in our solar system. In other words, KY Cygni is a living experiment in extreme astrophysics, offering insights that can't be gleaned from smaller, more stable stars. One major reason KY Cygni is so fascinating is its enormous scale. With a radius up to roughly 1,400 times that of the Sun, it stretches our concepts of size and distance. Its outer layers would engulf the orbits of inner planets in our solar system if it replaced the Sun, and the sheer volume of its atmosphere, filled with massive convective cells, makes it a prime example of how matter behaves when gravity and radiation interact on a colossal scale. Studying the motions of these layers allows astronomers to test models of convection, pulsation, and energy transport in stars that are at the very edge of what stellar physics can describe. Another point of fascination is KY Cygni's instability and variability. Its semi-regular pulsations and massive stellar winds illustrate the complex interplay between gravitational forces, thermal pressure, and radiation pressure. These pulsations not only change the star's brightness but also affect mass loss rates and shape its circumstellar envelope. Observing these processes in KY Cygni helps astronomers refine their understanding of how massive stars lose mass, an important factor that determines their ultimate fate, whether they become neutron stars, black holes, or even pair instability supernovae in extreme cases. Every observation of its variability provides real-world data to test theoretical models that were previously based on assumptions or smaller-scale stars. KY Cygni is also valuable for studying the late stages of stellar evolution. Red supergiants like KY Cygni are approaching the final phases of life for massive stars, during which nuclear fusion in their cores is running out, and complex instabilities arise in their outer layers. Because these stars evolve relatively quickly in astronomical terms, observing KY Cygni offers a snapshot of a transient, critical phase that is essential for understanding how massive stars die. Its observations provide a preview of the conditions leading to a core collapse supernova, one of the most energetic and violent events in the universe, giving astronomers a chance to test their supernova models before the explosion occurs. The massive atmosphere and circumstellar environment of KY Cygni also offer insight into the physics of gas and dust in extreme conditions. Its extended envelope, riddled with convective plumes, shocks, and ejected material, is a laboratory for studying how turbulence, radiation pressure, and stellar winds interact to move matter across enormous distances. This has direct implications for understanding how galaxies are chemically enriched over time, as massive stars like KY Cygni are primary contributors of heavy elements. By analyzing the structure and motion of the ejected gas, scientists can better model stellar feedback mechanisms that influence star formation and the evolution of galaxies. KY Cygni is further fascinating because it pushes observational techniques to their limits. Resolving a star thousands of light-years away, mapping its pulsations, and detecting its dust and gas envelope require cutting-edge technology like interferometry, infrared space telescopes, and radio arrays. Each observation demands careful calibration and interpretation, and the star's variability adds an extra layer of complexity. In this way, KY Cygni is not just a subject of study, it is a testbed for astronomical methods, helping astronomers refine their instruments and techniques while simultaneously advancing our knowledge of stellar physics. Additionally, KY Cygni challenges our understanding of stellar structure and mass limits. Its immense size, combined with relatively low surface temperature, defies simplistic correlations between radius, luminosity, and temperature. Studying KY Cygni helps astronomers probe the limits of how large a star can become before it becomes dynamically unstable or loses significant mass, informing broader theories about the evolution of the most massive stars in the universe. Observations of KY Cygni also allow comparisons with other extreme stars, such as Betelgeuse, UY Scuti, and VY Canis Majoris, helping scientists determine whether these behemoths follow universal patterns or display unique behaviors based on mass, metallicity, or age. From a broader perspective, KY Cygni also captures attention because it embodies the sheer awe and wonder of astrophysics. It is a star so enormous and so distant that human intuition struggles to comprehend its scale. Its slow pulsations, enormous atmosphere, and the eventual supernova that awaits it make it a dramatic and poetic illustration of the life cycles of stars. Beyond the technical and scientific significance, KY Cygni reminds astronomers, and the public, of the staggering extremes of the universe, inspiring curiosity, creativity, and exploration. Finally, KY Cygni represents a bridge between observation and theory. Its extreme properties allow astrophysicists to test models of convection, mass loss, nuclear fusion, pulsation, and supernova mechanics. Every piece of data gathered, its brightness variations, atmospheric structure, spectral composition, and mass loss rate, feeds directly into our understanding of the physics that governs not only red supergiants but all massive stars. By studying KY Cygni, astronomers gain insight into the life cycles of stars that have a profound impact on the structure and evolution of galaxies. In summary, KY Cygni fascinates astronomers because it is an extreme star in nearly every respect. Enormous in size, massive in structure, dynamic in behavior, and crucial in its role within the galaxy. It serves as a laboratory for studying pulsations, mass loss, extended atmospheres, and the late stages of stellar evolution. It challenges observational techniques, tests theoretical models, and provides insights into the creation of heavy elements and the processes that shape galaxies. Beyond its scientific importance, KY Cygni is a cosmic symbol of magnitude, complexity, and beauty, a star that embodies both the raw power of nature and the intellectual challenges that drive astronomy forward. This fascination naturally extends to public imagination, as KY Cygni and stars like it capture people's curiosity about the scale and majesty of the universe, bridging the gap between rigorous science and awe-inspiring wonder. Beyond the scientific allure of KY Cygni, there is a deeply human fascination with stars like it, an awe that transcends data, measurements, and astrophysical models. To the imagination, KY Cygni is almost incomprehensible. It is a star so vast that if it replaced our Sun, its outer surface would extend well beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, Mars, and even the asteroid belt. Trying to grasp its scale forces a humbling recognition of just how small our planet, and indeed our entire solar system, is in comparison. This sense of scale, combined with the star's vivid red glow, pulsations, and dramatic eventual fate as a supernova, ignites curiosity and wonder in the minds of people both within and outside the scientific community. Stars like KY Cygni have long inspired humanity to think beyond Earth and ponder the universe's enormity. Even without fully understanding the physics, simply knowing that such a massive, luminous object exists thousands of light-years away evokes a visceral reaction, a mixture of awe, humility, and inspiration. Artists, writers, and educators often use extreme stars as metaphors for power, scale, and the sublime. The concept of a star so large that it dwarfs our Sun and dominates its local environment taps into a primal fascination with extremes, reminding us of forces and scales far beyond our everyday experience. The public fascination is amplified by the dramatic stories these stars tell. KY Cygni is not just huge, it is a star living on the edge, burning fuel at a prodigious rate, pulsating, shedding massive amounts of material into space, and inexorably moving toward a cataclysmic supernova. This narrative of birth, life, and imminent death resonates with people because it mirrors universal patterns of creation and mortality, scaled up to cosmic proportions. KY Cygni becomes, in a sense, a cosmic character, a giant living its life in the Milky Way, with a story spanning millions of years, yet leaving observable traces for humanity to study. The dramatic redness of KY Cygni also contributes to its fascination. Red supergiants glow with a deep, orange-red hue caused by their relatively cool surface temperature, around 3,500 Kelvin. This color gives them a distinctly different visual presence than hotter, bluer stars like Rigel or Sirius, making them seem ancient, intense, and otherworldly. Astronomers and stargazers alike are captivated by this combination of enormous size and fiery, yet subdued, glow, which feels both beautiful and enigmatic. The red hue, combined with the star's massive envelope and pulsating brightness, reinforces the perception of KY Cygni as a living, breathing giant in the cosmos. Modern astronomy and media have amplified this public fascination. High-resolution images, simulations, and animations allow people to visualize KY Cygni alongside our solar system, comparing its size to the Sun and planets, which makes the scale both comprehensible and awe-inspiring. Interactive programs and planetarium shows often depict KY Cygni's pulsations, mass loss, and eventual supernova in ways that communicate the dynamic, extreme nature of the star. Even though the star is far beyond the reach of telescopic detail to the naked eye, these visualizations allow people to feel a sense of proximity and understanding, connecting human perception to cosmic scale. The incomprehensible mass and power of KY Cygni also spark philosophical reflection. Its eventual supernova, while harmless to Earth due to its 5,000 light-year distance, reminds us of the ephemeral nature of celestial objects and the immense forces shaping our galaxy. Stars like KY Cygni put human life into perspective. Our planet is tiny, our lifespan's fleeting, and yet we are capable of observing, studying, and understanding phenomena on scales that dwarf our everyday experience. This combination of vulnerability, curiosity, and intellectual achievement adds a profound dimension to public fascination. Culturally, stars such as KY Cygni inspire literature, art, and even popular imagination about space exploration. People are drawn to extreme stars as symbols of both the unknown and the extraordinary. In science fiction and educational storytelling, red supergiants often serve as settings, plot devices, or metaphors for scale and danger, further embedding them in collective imagination. The idea of a star so massive, so powerful, and so distant creates a narrative bridge between rigorous science and human creativity. The fascination also stems from the sheer improbability of observing such an extreme object. KY Cygni is rare, only a few red supergiants of comparable size exist in the Milky Way, and its combination of mass, variability, and evolutionary stage makes it a unique laboratory. Knowing that astronomers can measure, model, and visualize such a star, and that its life and death contribute materially to the galaxy, enhances the sense of wonder. KY Cygni becomes not just a star but a window into the universe's extremes, a tangible reminder of the extraordinary possibilities embedded in cosmic evolution. Finally, KY Cygni's story emphasizes a connection across time and space. Its light takes 5,000 years to reach Earth, meaning we see it as it existed 5,000 years ago, long before recorded human history. Its future supernova, while distant in time relative to our lives, will be observable across the galaxy and a spectacle for future generations. This temporal and spatial connection, the ability to witness events unfolding thousands of years in the past or future, enhances the public sense of wonder and underscores the interconnectedness of the universe. In summary, stars like KY Cygni capture the public imagination because of their incomprehensible size, vivid color, dynamic behavior, and dramatic life cycle. They evoke awe, curiosity, and humility, inspiring both scientific inquiry and creative expression. KY Cygni embodies extremes in scale, power, and beauty, serving as a bridge between human perception and the vastness of the cosmos. Its story reminds us of the grandeur of the universe and our small, yet remarkably observant, place within it. This fascination naturally flows into a broader perspective, reflecting on the scale of the universe and our place within it, which is the ultimate takeaway from contemplating a star as immense and extraordinary as KY Cygni. Reflecting on KY Cygni in the grand context of the universe brings a profound sense of perspective, one that combines awe, humility, and curiosity. This single star, so distant and immense, serves as a stark reminder of the sheer scale and complexity of the cosmos. Its radius, stretching up to 1,400 times that of the Sun, dwarfs entire planetary systems. Its mass and luminosity, while impressive, are just one instance of the forces that govern galaxies and the life cycle of stars. Observing and understanding KY Cygni forces us to confront the fact that our everyday experiences, limited to the tiny scales of Earth and the solar system, occupy an almost infinitesimal fraction of cosmic reality. The story of KY Cygni also illustrates the dynamic, evolving nature of the universe. It is not a static monument in space. It is a living, breathing star, pulsating, shedding mass, and driving chemical evolution across its neighborhood in the Milky Way. The dust and gas it ejects today will, millions of years from now, seed new stars, planets, and perhaps even the raw materials for life. Its ultimate fate as a supernova will release enormous energy, reshape its surroundings, and continue the cycle of creation and destruction that has persisted in galaxies for billions of years. In this sense, KY Cygni is both a singular object of immense scale and a participant in the cosmic dance of matter and energy. Considering KY Cygni also highlights the limits of human perception and comprehension. Even with our most advanced telescopes, space-based observatories, and interferometric techniques, we are only beginning to grasp the details of its structure, atmosphere, and variability. Its immense size, complex pulsations, and extended envelope of gas and dust challenge our models of stellar physics, pushing the boundaries of theory and observation. And yet, despite these challenges, we can measure, map, and predict aspects of its behavior, a testament to human ingenuity and the drive to understand our universe, no matter how immense or seemingly incomprehensible. The star's temporal dimension adds another layer of reflection. Light from KY Cygni takes roughly 5,000 years to reach Earth, meaning we see it as it existed millennia ago, long before modern civilization emerged. Its eventual supernova, while distant and not threatening to Earth, reminds us of the timeless and patient processes that govern the cosmos. Stars live and die on timescales far beyond human lifetimes, yet we can witness, study, and learn from them. KY Cygni embodies both the longevity and the impermanence of celestial objects, contrasting sharply with the brief, fleeting nature of human existence. From a philosophical perspective, KY Cygni illustrates the interconnectedness of all things in the universe. Its heavy elements, forged in nuclear reactions over millions of years, will eventually contribute to the formation of planets, stars, and even life elsewhere in the galaxy. Every atom of oxygen, carbon, or iron in our bodies may have originated in a massive star similar to KY Cygni. In contemplating the star, we recognize that our existence is intricately linked to processes unfolding on vast scales, spanning distances measured in thousands of light-years and timescales measured in millions of years. It is a humbling and inspiring realization. We are small in scale, yet intimately connected to the cosmos through matter, energy, and shared history. KY Cygni also provides a mirror for human curiosity and ambition. By studying it, we push the boundaries of technology, mathematics, and theoretical physics. We develop instruments capable of resolving surface features on stars thousands of light-years away, interpret signals across the electromagnetic spectrum, and refine models of stellar evolution, mass loss, and supernova mechanisms. In this pursuit, KY Cygni is both a challenge and a teacher, showing us what is possible when curiosity meets perseverance. It reminds us that understanding the universe requires imagination, rigor, and a willingness to grapple with phenomena far beyond our everyday experience. Finally, KY Cygni's presence in the cosmos instills a sense of wonder and humility. It is one star among hundreds of billions in the Milky Way, yet it is so enormous, so extreme, and so complex that it dwarfs our comprehension and imagination. Contemplating KY Cygni encourages reflection on our own place in the universe, not only as tiny observers on a small planet but also as participants in a grand, ongoing story of cosmic creation, transformation, and renewal. It is a reminder that the universe is vast, powerful, and full of phenomena that challenge and inspire us, inviting endless curiosity and exploration. In conclusion, KY Cygni is more than just a red supergiant. It is a symbol of the scale, power, and beauty of the universe. It teaches us about the physics of extreme stars, the processes that shape galaxies, and the intricate recycling of matter that sustains cosmic evolution. At the same time, it reminds us of our tiny place in the grand cosmic scheme, inspiring humility, awe, and wonder. By studying KY Cygni, observing its light, and contemplating its life and eventual death, we gain perspective on the universe and our connection to it, and we are reminded that even the smallest beings on the tiniest planet can reach out and grasp the immense truths of the cosmos. KY Cygni embodies the ultimate lesson of astronomy. The universe is vast, full of extremes, and both humbling and inspiring, yet through curiosity, observation, and study, humanity can begin to comprehend even the most incomprehensible giants among the stars. It stands as a beacon of cosmic perspective, showing that while we are small in the universal scale, we are capable of understanding, marveling at, and even celebrating the immense forces that govern the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.